Dear students, in this video, we are going to discuss gain directivity of reflector antennas.
Is Georgia. Okay, so here what is the primary antenna here it is? We are using R. Okay, so this is a parabolic. Okay, so this is a parabolic. Okay, so the opening of the open end of the paraboloid is called as aperture. The open end of the paraboloid is called as aperture. Okay, so by using this, we will get the pencil beams. Okay, very high gain beams. Okay, particular means it will radiate particularly in that direction. Radiates. So by using this type of parabolic reflector shape, we will get the pencil beams. We get the pencil beams. Okay, so we get the pencil beams. Okay, so let us consider, for example, the power gain. The power gain. The power gain with the circular aperture. With the circular aperture. Okay, so for example, let us take this is my parabola. This is, let us consider this is my parabolic antenna. Okay, so here I am keeping my primary antenna. So this distance, okay, so this distance from this parabolic to this distance is focal point. Okay, and this is called as the D, diameter of the circular aperture. D is diameter of the circular aperture. So this is nothing but if you draw like this parabolic aperture. So the D is the open end. This D is the diameter of the circular aperture. So the power gain, here I am considering the primary source as dipole antenna. So I am considering it as dipole antenna. So for half wave dipole, it is given as GP is equal to, you know that what is the relation? P is equal to 4 pi AE by lambda square, which we have already derived. Okay. So power gain means what is the major relation between directivity and power gain? In directivity, we'll consider only the power radiated, but in power gain, we'll consider the loss also. Okay, so GP is equal to 4 pi into A naught by lambda. What is this A naught? For example, this is my perfect parabola. Only let us consider this portion is effectively receiving the electromagnetic, receiving or transmitting the electromagnetic. What about this region? It is not actively transmitting. So physical size is represented with A. A is represented with physical size. A naught is aperture area. A naught is effective area. Okay, so always A is always greater than A naught. Okay, so GP is equal to 4 pi A naught by lambda square, where A naught is effective area. Where A naught is effective area. And what is the relationship between A naught and A? So A naught is equal to K into A. Okay, so A naught is effective area, A is physical area. Physical area. Then what happened to the K? Always the physical area is more when compared to the value of K is equal to A naught by A. Okay, so this is the effective area, this is physical area. Always the value of K is less than 1. The value of K is always less than 1. So effective area is always less than physical area. So the value of K is always less than 1. So here you are taking the primary antenna or it is dipole. Okay, so it is a dipole. So for a dipole, the value of K is equal to 0.65. Very important thing you want to remember. For a dipole, what is the value of K? It is for a dipole field, the value of K is equal to 0.65. Okay, so the value of G is equal to 0.65. Therefore, GP is equal to 4 pi In the place of A naught, I will replace with K into A. Okay. So K into A by lambda square. K into A. Where what is this A? A is area of circular aperture. So it is pi r square. Or I can write it as pi d by 2 whole square, where D is the diameter of circular aperture. D is the diameter of circular aperture of parabolic reflector. Parabolic reflector. Therefore, GP is equal to 4 pi into what is the value of K. If it is a issue of feed antenna is dipole, it is 0.65 into pi d square by 4 pi lambda square. So therefore, GP is equal to 6 d by lambda whole square. This is very, very important. 6 d by lambda square, where the fraction d by lambda is called as aperture ratio. The ratio of field focal length d or diameter d to lambda is called as the ratio. This ratio is called as aperture ratio. Is called as aperture ratio is called as aperture ratio. So d by lambda is called as aperture ratio. So d by lambda is called as aperture ratio. Okay, so this is okay. Next, the beam width between first nulls. Okay, so for example, let us take this is my parabolic reflector. This is my parabolic reflector. Okay, so this is my first null. This is my first null. Okay, so what we call the angle between the first nulls? So if this is my radiation pattern, if this is my pencil cut radiation pattern, okay, so this is my null. So this angle is nothing but what is this angle? This angle is so the angle between these two nulls. Okay, so the angle between these two nulls. Okay, so this angle between these two nulls. The angle between these two nulls is nothing but beam width between first null. So similarly, how to indicate half power beam width? So when the power has fallen to half of the maximum. Okay. Okay. So this angle, let us consider here the power has fallen. So this is half power beam. This angle, whatever this angle here, it is called as half power beam width. Okay. So assuming for larger aperture, the beam width between first null can be expressed for a parabolic antenna, can be expressed as for a parabolic antenna. For a parabolic antenna can be expressed as beam width between first null is equal to 140 lambda by d degrees. 140 lambda by d degrees. Okay, so where lambda by d. Okay, so similarly, half power beam is 58 lambda by d in terms of degrees. So half power beam is equal to 58 lambda by d. Okay, so 58 lambda by d. For example, if for example, next for uniformly illuminated for uniformly illuminated uniformly illuminated aperture. means if all the portion of the paraboloid is utilized effectively. Okay, so every portion is utilized effectively, then the directivity is equal to 4 pi AE by lambda square. Here, effective area is equal to physical area. Effective area is equal to physical area. Because we are assuming that all the portion is, for example, it is not practically realizable. But if every portion of the reflector is effectively utilized, okay, so where A is equal to pi d by 2 whole square. Okay, so the directivity is equal to 4 pi into pi t square by 4 pi lambda square. Therefore, the directivity is equal to 9.87 d by lambda square. Okay, so see the difference. Here, this is power gain. Here, what is the assumption you have assumed that here only some portion of the physical effective area is utilized, okay, not complete portion, okay. So only this portion is effectively utilized, and this portion is not utilized effectively. This portion and this portion is not utilized. So this A indicates physical size and A not indicates the effective area. Okay. Here gain is also considered, that is power gain. Okay. But here in this case, all the portion from here to here, each of the portion is effectively utilized. In that case, the directivity is 9.87 into d lambda by whole square. D lambda by whole square. D lambda by whole square. Okay. So the very important, the open end of the parabolic reflector is called as the open end of the open end of the parabolic reflector. The open end of the parabolic reflector is called as aperture. Is called as aperture. Okay.